Muy bien, ya estamos al aire, ¿verdad? Buenas tardes. Ok, um, Aarón, Aarón, ¿podrías decirnos, ya estamos al aire, ¿verdad? Okay, so thank you, everyone. Today we are starting the QMexico webinar. Um, Thank you for attending this event, and I want to introduce Andrea Delgado, who is a researcher in Oak Ridge National Laboratory. Welcome, Andrea. And so, for people, please put your questions on YouTube. And at the end, we are going to discuss with Andrea. So, thank you. Go ahead, Andrea. Hi, hi.
Thank you. I'm very excited to be here today. I'm excited about these new initiatives in Mexico on quantum computing. And feel free to drop your questions anytime during the talk. I reserve a few spots during the slide to just stop and take a few questions. I would like to start my talk today by telling you a little bit of the history of Oak Ridge National Lab. It was funded during the Second World War, and it was established as a place where they would enrich uranium for the atomic bomb. And it stayed that way for a couple of years until the end of the Second War. And right now it's one of the 17 DOE national labs in the US. And a couple of things haven't changed in Oak Ridge, the city, since 1942. We still have a population of close to 29K, and the scientific goals of the lab are still the same. We're still interested in world peace and national security. Some of the pictures that I'm showing here include one of the stars of the Manhattan Project, such as Wigner and Oppenheimer. This is what Oak Ridge National Lab looks like today. It's the largest DOE national lab by size and the third one by funding. And currently the scientific program focuses not only on materials and neutron science, but also in high performance computing, biology, and national security. And more recently, the last decade or so, we also have a strong program in quantum information science. Some of the scientific facilities at Oak Ridge include the spallation neutron source and the high flux isotope reactor. And Oak Ridge is also home to the second most powerful supercomputer in the world, Summit. And my talk today will be focused on high energy physics. And although the lab doesn't have a strong tradition on high energy physics, it's mostly on nuclear physics and detector R&D specifically for nuclear physics experiments. We're trying to change that, and I'm hoping to give you an idea of our goals for the next decade or so. And just so that we're on the same page, since I don't know if your background or how familiar you are with high energy physics. High energy physics is the branch of physics that really tries to answer the question, what is the universe made of? And if it's made of something, what are these building blocks? And what holds these building blocks together? And so the knowledge that we have right now is embodied into the so-called standard model, which is the diagram that I have on this slide. And it's composed of some particles, the matter particles, such as the quarks and the leptons, and the mediator particles, such as the photon and the gluon, and most recently, the Higgs. Now, depending on your take, you might or might not say that the standard model has been very successful. I think it has been. But so far, all the experimental data that we have is consistent with the standard model. Now, despite the success of the standard model, there are still some questions that the standard model doesn't provide an answer to. For example, why is there more matter than antimatter in the universe? The standard model doesn't provide a candidate for dark matter. We still don't understand how the mass of neutrinos came to be and why the interaction is only left-handed. and many more questions. I will run out of slides if I were to add all of the potential probes to the standard model. But particularly on this slide, I would like to highlight some of the experiments at the physics division at Oak Ridge that are trying to understand or expand or probe the standard model in some way. So we have the neutron EDM experiment at the SNS. We have neutrino detectors in the HIFA reactor and also at the SNS in the so-called neutrino alley. And just to give you an idea of the high energy physics environment in the US, because there's so many projects that could be funded. So just to give you an idea of who gets the shots on calling what kind of projects are funded. In the US, we have the so-called particle physics prioritization panel, the P5 for short, which is a sub-panel of the high energy physics community, which serves in some way as a panel that recommends the funding agencies such as the Department of Energy and the National Science Foundation in what kind of physics projects, particle physics projects to invest over the next 10 years or so. And in 2014, the first P5 report came out where 5 science drivers were identified, including the use of the Higgs boson as a tool for discovery, the pursuit of the physics associated with the neutrino mass, identify the physics of dark matter, understanding cosmic acceleration, and exploring the unknown in general, so new particles, new interactions, and physical principles. So any particle physics project funded in the US right now falls into one of these 5 categories. So before the P5 project is, I guess, released, the project before, the exercise before that is called SNOWMASS. So currently we have this SNOWMASS exercise, which is a long year effort where the particle physics community gets together and forms groups according to the particular interest of the group and try to identify and more specifically to document the scientific vision for the future of particle physics and also its international partners for the next 10 years or so. So on this slide, what you see are the different frontiers that have been identified for SNOWMASS. And each one of these frontiers has subtopics. And in particular, I would like to bring your attention to the computational frontier because for the first time, quantum computing has been added to the SNOWMASS process as one of the areas that the high energy physics community should invest on. And the ORNL contribution to SNOWMASS had a very big impact as we had Dr. Travis Humble as one of the conveners for the subtopical quantum group. I gave a presentation on the data analysis in high energy physics with quantum computers, so an overview of what I do and what some of my colleagues do. And Travis also gave a talk on co-designing for high energy physics from an outsider perspective. And we also submitted a couple of letter of intent. So I must say that about 30 letters of intents were submitted to SNOWMASS, and Oak Ridge submitted or authored at least 6 of them. So I would say 6 out of 30, it's a big contribution. And these letters of intent are some sort of part of the documentation process that will go into the P5 report after the end of SNOWMASS in 2021. This first part of my talk was just to give you an overview of high energy physics in general. And on this part, I will now like to focus on why quantum computing and more specifically, why quantum computing for high energy physics. In terms of experimental facilities for high energy physics in the 2020s, we have in the energy frontier, the LHC and its planned upgrades to eventually become the high luminosity LHC. We have DUNE, which will be the largest neutrino experiment ever built and which is expected to start taking data in 2025. In the nuclear physics / medium energy frontier, we have the Electron Ion Collider, which will be a one-of-a-kind nuclear / medium high energy physics research facility. And I'm showcasing these facilities here because Oak Ridge has a strong involvement in this experiment, but also to give you an idea or like try to bring the point of what these experimental facilities have in common. And what they share in common is that all of them have complex detectors that produce large data sets that are usually hard to collect, process, and also analyze. And this is where the computational frontier comes in. Since we have so much data and so many new and rare processes to not only see, but also maybe simulate, the new tools such as machine learning and quantum computing come to help into this field to enable or accelerate scientific discovery in high energy physics. Now at Oak Ridge, we are on a very privileged position because we not only have access to the facilities and the data, but we also have the computational resources through the Oak Ridge Leadership Computing Facility. So as part of ORNL, we have access to high performance computing such as Summit, and also quantum computing processors such as D-Wave and IBM through the OLCF. And just to zoom out again out of Oak Ridge and to the national perspective, the US is investing a lot on quantum information science. If you're not aware, in 2018, the White House signed the National Strategic Overview for Quantum Information Science. And just recently, on August 26, the White House announced the formation of 5 centers in the US with 125 million for each center to dedicate to the study of quantum information science. And Oak Ridge was really lucky to get one of these centers. In terms of high energy physics, the Department of Energy has already identified fundamental high energy physics areas that could potentially benefit from applications. So not only on the data analysis side, such as quantum machine learning and data analysis methods, but also in terms of the simulation of quantum systems. So some areas that are currently being explored include black hole physics, trying to understand quantum gravity and entanglement in general. So the DOE is really funding these ideas to try to identify where quantum computing could accelerate discovery in particle physics. So there's already several national labs exploring applications in high energy physics, such as Brookhaven, Fermilab, and more recently, Oak Ridge. And with that, I would like to stop here to see if there's any question, because from now on, I will move into like more of a technical part of the talk. So if there's any questions so far.
No, no for the moment.
No questions?
No questions.
Okay. So what is quantum computing? And today I will only be giving like a very high level overview, layman's explanation of what quantum computing is, but feel free to ask me in detail if you want anything, if you want me to go in more detail. So quantum computing is basically the use of quantum mechanical phenomena such as superposition and entanglement to perform a computation. So currently there are 2 main approaches to physically implement this principle in quantum computing. So the first one is the so-called universal quantum computing, where we have a series of quantum gates that operate on a set of quantum states. And the processors that use this principle include the ones provided by IBM, Rigetti, Intel, and Google. And we have the second kind, which are the quantum annealers, which take or perform these calculations through the evolution of a quantum system to a ground state. And one example of this is the D-Wave processor. In Japan, they have also a digital quantum annealer, but it's also some sort of like a hybrid quantum annealer. And for today, for simplicity, I will only focus on quantum annealers because the other kind of processors involve more, it will involve me to get more into the details of quantum computing, linear algebra, and all that stuff. So the basic of quantum annealing, what kind of physical principle makes quantum annealing work? And that is the adiabatic theorem. And this theorem tells us that a system will remain on the ground state as long as the perturbations that we apply act slowly, and as long as there is a gap between the ground state and the rest of the system's energy spectrum. So if we had to write a recipe for this theorem, we will have something like this expression on the gray box. So we would encode our solution into our H1 Hamiltonian, and then we will also prepare an initial Hamiltonian H naught, which will consist of a well-known physical problem, or which has a ground state that it's usually easy to compute. And then we will slowly evolve our system from H naught to H1. And at the end of this process, the system will be in the ground state encoding the solution to our problem. In particular, on D-Wave, this is performed through circulating currents. So the qubits, or the fundamental processing unit, are circulating currents which are on either state 0 or 1, or up or down, whatever you want to call it. And these states are prepared through some sort of magnetic fields, and then we apply a bias weight into these qubits, so that we bias the probability of the system to be in one state or the other, because before that we have these two qubits in superposition, so it can be in either one state. But really the power of quantum computing comes from having a system of qubits, and we sort of entangle or connect these qubits by using a coupler with a string that can be modified by the user, so that at the end our system, or sort of the solution that we encoded in the system, is performed through what we call an objective function, O, which will be your quantum machine instruction. And so the general game strategy will be to formulate our classical problem that we want to solve, particularly an optimization problem, or the solution to a Hamiltonian, as a QUBO problem, which is a quadratic unconstrained binary optimization. And by formulating our problem as a QUBO, we can solve our system or our optimization problem through quantum annealing through D-Wave. And to showcase some of the applications, the current applications to high energy physics, I would like to focus today on jets, because that's my particular area of expertise and my preference as for analysis tool in high energy physics experiments. And the first application is the color recombination problem. The color recombination problem tries to answer the questions, or to figure out how the particles, quarks and gluons, regroup or form another bound state after the QCD confinement is broken after a high energy collision. And they must do so in a way that the color is conserved. And if you're not familiar with color, it's some sort of analogous to the electromagnetic charge, but instead of having positive and negative, you have three colors. So before color recombination, for example, if you have two protons which have quarks and gluons inside them, after the collisions, these quarks and gluons will try to form another bound state. So really simulating this process, it's really computationally hard because you need to optimize or find a solution that optimizes this recombination in a way that minimizes the energy of the system. And so in terms of computing, you have to do a permutation over all the possible combinations of these particles according to the SU3 color rule, which tells us which connections are allowed. And this is where quantum computing comes in. We cast this color recombination problem as a traveling salesman problem. And if you're not familiar with this formulation from graph theory, the traveling salesman problem is a problem of finding the route that minimizes the distance traveled. So if we have a number of cities, we want to visit all places at once, returning to the starting point, and we want to find the route that takes us from home to all the cities and back with the minimum distance traveled. And in this quantum color reconnection formulation, we find a system configuration that minimizes the sum of the edges, where each edge is weighted with the coupling strength between the particles, in which follow the SU3 reconnection rules, and we must include all the particles in the system. And then we simplify our life by not allowing only gluon connections. We need to have bounces that include one quark and an anti-quark. So I guess in the phenomenology terminology, we stayed into like the baryon physics first order Feynman diagrams. And after we find one system, the connection from the ending particle to the other, the weight that we assign there, it's 0. So we know where to break the loop and form composite particles. And these are the actual results from running on D-Wave. So what you see on the plot on the top left side of the slide is the number of nodes or the number of qubits that we need to solve this problem on red, and the number of edges or the number of connections that we need to solve these problems. And the x-axis is the event number. It's just, I guess, the name of the event. It doesn't stand for like the number of particles on the event, but these particles, the size of these events ranges from 10 to 17 particles, so it's really a small size, but the number of logical qubits that we need to solve this problem, it's very large and it grows almost exponentially. And the reason that this happens is because the chimera graph, or the way that qubits are connected on the physical system, has the mapping that you see on the bottom. So for example, if you encode your logical variable into your physical 0 qubit, you won't be able to connect to all of the qubit. The qubit 0 doesn't connect to 1 or 2, but you need to form chains between the qubits to have your problem encoded into this processing unit. And what you see on the right is the solutions that we get from running on the quantum annealer. The red line is the solution, the true ground state solution to this problem. And this plot is just to show you the range of solutions that we get. So we don't get the solution that we're looking for 100% of the time. And for some cases, we don't even reach the ground state. And the difference between the gold boxes and the blue boxes is the blue boxes are the problems that were solved specifically on the QPU, and the left one, the solutions that we get from a simulation of a quantum computer. So we see that the quantum computer actually performs better than the simulation. And just to give you a scale of the time to solution for this kind of systems, these different formulations range from less than 1 second to 100 seconds per anneal or per event, depending on the workflow or the processor that we use. And for some cases, since the size of the problem that we are trying to embed on the QPU is very large, we use a hybrid formulation or a hybrid embedding on the QPU. So what we do is to break a problem into smaller pieces that are more suitable for the QPU device, and then solve that small subproblem on the quantum computer, and then try to solve a different fraction of the problem by classical methods such as simulation or exact methods. And then we iterate a few times and try to see what gets us the best solution, and then just compose the problem again. Now, jets. So if you're not familiar with jets, jets are pretty much the detector observables or the quarks and gluons in a collider experiment. And it basically is a collimated spray of the particles that result from the hadronization or the regrouping of the quarks and gluons after the QCD confinement is broken. And we study jets or this collection of particles as a whole in a hope to have an idea of the kinematical properties of the initial particle, either the quark or the gluon. Now, jets are very important analysis tools in CMS and Atlas. According to Inspire, more than half of the papers that were published by these two experiments make use of jets. And currently, there are several ways to reconstruct or to make up this so-called analysis tool jets from the detector observables, meaning the calorimeter towers or the tracks coming from the tracker, so the silicon strip hits. But this task is usually very computationally intensive because we need to perform optimization over a large number of final state particles. And if you're not familiar with experimental high energy physics, this plot will give you an idea of how many particles we need to cluster or to group into different jets according to the kind of interaction. So starting from hadron collisions, so proton-proton, all the way to lead-lead collisions. There's usually two approaches to jet reconstruction. The first one is the so-called cone algorithms, which is the top-down approach, and this is the preferred tool for phenomenologists because the tools, the observables that you see from these cones, if you want to perform jet substructure analysis, this will give you a better insight of the initial particle. And they usually work by identify large regions of energy flow, meaning that you find a stable cone. So the jet axis will coincide with the sum of momentum of the particles that are forming the jet. But this is also very computationally expensive. So it takes at least an order of magnitude longer to run in no matter what number of particles you have in your system. And the preferred choice for experimental high energy physicists is the sequential recombination algorithms. I know that at CMS and Atlas, the preferred choice is the anti-KT. And these are so-called bottom-up approach. So you start by combining particles from the closest one. You choose a distance measure between them and start just recombining and forming groups. And this in general give a better CPU performance. And in order to make these computations faster, we're looking at the option of using quantum computing for clustering. So the first idea that I came up with was to use a quantum version of the K clustering algorithm, which is has been used in machine learning for a long time. And in this way, we can still use a distance measure such as the anti-KT, which takes the difference in eta and phi. So the plane that it's perpendicular to the beam axis divided by the cone radius of the jet. And by minimizing this distance, we will have an assignment to a particle to one of these clusters. And this is what the objective function to be solved in a quantum annealer will look like. We also have a penalty term to enforce the one-hot encoding, meaning that only the particle will be assigned to only one of those clusters and not two. And I'm currently working on implementing this algorithm, but depending on how good the results are, the jet size and the mass of the jet and other phenomenological observables that we look at, we might add additional physical constraints, meaning more terms to this Hamiltonian, which might include the W mass in the top quark reconstruction, for example, to make this algorithm more accurate. A second version is the quantum version of the single cone algorithm. And the single cone algorithm has been used in E plus, E minus colliders for a long time now. And basically what it tries to do is to find an axis of a cone and then just cluster all the particles with a radius given by the user and just take all the particles that fall into that cone by minimizing a quantity that it's called thrust. So the value of thrust will tell you how pencil-like your system will be according to the axis that you use. Now, for future work, we will have this formulation generalized to more than one jet, because the single cone jet only gives you one jet, and this is not very suitable for high energy experiments where we have a large number of jets. And we have a very early formulation of what this generalization would look like, but in the Q form on the actual physical implementation, we can carry this double summation, so we need to simplify this expression a little bit more. Now, as a summary of my talk, today I hopefully introduce some of the applications of how quantum computing might enable scientific discovery in high energy physics. And I presented a few algorithms focusing on jet clustering. And the algorithms that I presented today can be solved in quantum annealers, but we're also working on a different formulation on gate-based computing using the Grover search. Also today I focus specifically on jets, but I am also working on quantum machine learning applications for classifications and reconstruction of neutrino events. I'm also working on track reconstruction using quantum computing. And this is I hope I'm motivated that this is a very interesting project because it's very interdisciplinary, because it hits in two very interesting fields. For example, from physics, we would like to find a better way to cluster these particles and to study these rare events, specifically now that the LHC is, the high luminosity LHC is coming. And we hope that we don't have to trade physics performance for CPU performance. But also from the quantum computing point of view, by doing these studies, we can benchmark quantum computing devices for optimization problems in general. So from my perspective, as a high energy physicist, we are a field that it's running out of options. And the physics reach that we can have for future experiments will be limited by how efficiently we use our computational resources. So everybody right now is thinking in GPUs and heterogeneous computing in general, but I really think that quantum computing, it's worth a shot. And we really don't have to prove quantum supremacy. We can do hybrid algorithms. I've seen people doing hybrid machine learning where you do the pre-processing classically and then the part where the quantum computing is better, then you run that part of your workflow on a quantum computing. But in order to take advantage of all these tools, we really need to start identifying the strengths and the weaknesses of these systems. And that's all I have for my presentation. But if you have any questions, feel free to just drop them in the chat or reach out. This is my work email, so feel free to send your questions if you want to chat. Thank you.
Okay, thank you, Andrea. Very good, very nice. I think for me at least, this is a very exciting topic to do research. So we have one question, at least at the in this moment. Bruno said, "Do you use any specific libraries to program the quantum annealer, such as Qiskit or anything similar?"
No, but yes and no. In order to program a quantum annealer, you need to do your Q formulation. So you can do it like pretty much by hand by using Python or NumPy, or there are some libraries already that take your Hamiltonian into a Q form, but these are all Python based. In order to submit your problem to the actual quantum processor, you only need one line of code. So you install Ocean, which is the SDK of D-Wave, and you just call one line, which is like model equal submit Q, and that's it. It returns a NumPy array.
Okay, so we have other question is why do simulations perform worst?
Perform worse in terms of physics or CPU?
Yeah, it's not clear the question maybe, but maybe Edgar, could you explain more the question, please, Edgar? So, okay, I have a question. I have a question. In the 23 slide, did you put a split or yeah separate? Considering that you use classical quantum computing or quantum computing. So my question, yeah, perfect. Thank you. So my question is, how you can separate, or what is the criterion to separate the simulation or the formulation of the problem?
So the
Yeah.
formulation of the problem is the same. You have your problem in a cubo form, but D-Wave SDK is software development environment allows you to use a quantum simulator. You can use a taboo solver or simulated annealing to solve your
Okay.
problem, or you can send your problem to the quantum processing unit.
Okay, okay. Maybe this is not clear for me. In the composition there, you have to separate in classical computing and quantum computing. There, do you have, I mean, maybe a trigger or something like that to separate?
Um, I think you're talking about, I was focusing on the top plot, but the diagram
Okay.
on the bottom is actually a hybrid. So the ones on the top are either classical or quantum, and then the
Okay.
one at the bottom is hybrid. So you decompose your problem into sub problems, and you can choose how you want to solve it. So you can tell the device just run on like 1/3 or 1/4 of my problem, and then use classical ways to solve the rest of the problem or the entire problem, and then it compares which one gives me a solution that is lower in energy, and then takes the best. But that's totally like user defined. If you want to run it for like a week and run it 1,000 times, that's fine, it can do it. Or if you want faster, then you can just assign whatever way you want to solve it.
Okay, okay. We have another question is quantum error correction used at a lot or not?
Yes, for the gate-based architecture, or at least from the user side, because D-Wave, of course, it's also a noisy device. It's not perfect, and most of the times you run into problems like you form an embedding for your problem, and then the next day one of the physical qubits is like off, so you have to reformulate your embedding. But most of the noise control on D-Wave devices is made on the D-Wave side. Whereas if you're programming on an IBM computer, for example, you need to create your own way to correct for noise. So you run tests where you know the actual ground state or like the solution of your problem, and then you compare to other cases and then try to extrapolate where there is noise in the system in a statistical way.
Okay, perfect. So we have other question is what's the path from physics degree to work on a laboratory like Outreach Lab? There is other one. What do you need to know? I mean specializations on topics to study. She's a or he is a physics student, so maybe he's looking for or she's yeah. This person wants to know more about the opportunities to work in a laboratory as you, Andrea.
Um, yeah, so I must say I'm a physicist by training, so I don't have a degree on quantum computing or in computing at all, but I feel like during my PhD program, I always focus on the software development side. Um, I always work on tools on jet reconstruction, how to calibrate the energy of these jets. So I spend a lot of time coding. I studied from Fortran all the way from C++, Python. I'm starting to learn Julia now.
Yeah.
But if you want to go into quantum computing, I don't think there's like a defined path right now because there's also like no degree that I'm aware of. But you really must like coding and like going through like all the bugs in your code, but also having, I guess, sort of this problem solving skills.
Okay, thank you. So we have other question is, do you know if there is any group in Mexico building a QC or quantum computing? Yeah, okay, Andrea, please.
Uh, I'm sorry, I don't have the answer to that. So one thing is building a quantum computer, and
Ye-
one thing is just like, I really have no big insight on how the physical implementation of quantum computer works. I just work on the algorithm side. So I wouldn't be surprised if there's more than one group working on applications, but as far as building an actual quantum computer, I'm not so sure. That's outside of my area of expertise.
Yeah, in fact, this is a very good question because there are different communities or initiatives working on quantum computing. But as Andrea mentioned before, we need more investment in this kind of topics. At least in Mexico, I don't know if there is more communities working on to promote this kind of ideas between Latin America or among Latin American countries. Then, in my point is, I don't know, but we as a Mexico, we are a community promoving this kind of topics. So, okay, another question for Andrea. How much does it cost to build a quantum computer from scratch with all the knowledge we have? Do
I
you
have
know?
no idea. You could probably just Google the question.
But did you mention? I don't remember 100. Or don't remember 1,000 or there are million of dollars to.
Yeah, the US is one of the countries in the world that is investing the most in quantum computer. Quantum. It, the thing is, it's investing on quantum information science. But quantum information science involves the development of quantum computers, understanding entanglement, quantum teleportation, cryptography. So really quantum computing is only like a branch of quantum information science. So it will be hard to break down where that money is going.
Okay, so I have more questions. As a Mexican, for our audience, Andrea is Mexican, but she studied in Mexico, and sorry, in Texas University. Then, what do you think about Mexican community of science? So, I mean, do you think it's a good moment to invest in this kind of topics?
Absolutely. I am not very familiar with how research works in Mexico because I've spent most of my life in the US. But I follow really close this community of Quantum Hispano that it was formed after the Kiss Kids Summer School. And they really work hard. I think there's a lot of talent in Mexico, so we just need the good resources.
Yeah. Okay, other question. Which quantum computer is better for computations, D-Wave or IBM?
That's a hard question.
Yeah.
If you're starting from a non computational sciences background, I would say D-Wave it's sort of like a less steeper learning curve because pretty much you only have to work on the formulation. So you have your optimization or Hamiltonian problem, and then you just put it into cubo form and just call one line, and then it's solved. For gate-based computers, you actually need to learn to program, and you need to have a good understanding of your device because of what I was mentioning before of error correcting. So you can run on D-Wave, I would say, overnight if you have a problem in mind. If you want to program on Qiskit, it's hard. Um, but also IBM, it's promising like I don't know how many thousand qubits in 10 years. So if they actually are able to have such a large system, then we might see an advantage finally of using quantum computers.
Okay, thank you. There is more question. How is it like to develop academically in the USS as a Hispanic? Do you have many Hispanic colleagues?
Um, at Oak Ridge, not so many. The picture that I have here is my mentor, Dr. Galindo Uribarri, who actually went to UNAM, I think, and he has a large program of bringing Mexican students and Colombian students to Oak Ridge like every summer. Um, but I've been at Oak Ridge for 2 or 3 years, and before that, I was at Fermilab. And I must say, at Fermilab, the Hispanic community is like huge. It's very different than Oak Ridge.
Okay. There is one question in Spanish, so I'm going to talk in Spanish. Sorry if there is some people in other countries. ¿Se puede aplicar en trading? I don't know what is trading.
Trading, sí, de hecho hay un grupo que trabaja aquí en Oak Ridge en optimización de portafolios, como este no es de nuevo mi área de experiencia, pero de lo poco que he escuchado, pues es un poco machine learning porque es predicciones, stocks y todo eso, pero es una de las aplicaciones más grandes. En Estados Unidos hay bancos como Morgan, JP Morgan Chase, que ya están invirtiendo en computación cuántica para este desarrollo de portafolios.
Ok, qué interesante. Dice también análisis de mercados. Nos preguntan o comentan también. ¿Sabes tú algo al respecto?
La verdad no sabría, pero supongo que es parte del mismo dentro de la parte de economía.
Ok, ok. Ok, sirve para trading que ya nos habían preguntado, bueno, ya habían comentado. Okay, so I don't know if no sé si hablan español. Bueno, en los dos soy pésimo, la verdad, no mentiras. Pero bueno, con el ánimo de promover un poco también las preguntas en español. Ya nos preguntaron, ya te preguntaban, Andrea, cuál sería como el camino a seguir para una persona que está iniciando en estos pasos de la computación cuántica y que se ve a futuro como un investigador, en este caso como tú en un instituto en Estados Unidos, trabajando ya como una investigadora. Ahora, desde mi punto de vista, yo he visto pocas mujeres que se han incorporado en estas líneas de investigación. ¿Podrías contarnos un poco de tu experiencia bueno, bajo esta condición? ¿Qué tal es? Debe ser bastante chévere porque he visto también un poco un bajo porcentaje de mujeres trabajando en estas áreas.
Sí, de hecho es una de mis otras pasiones fuera de la física y de la computación cuántica. En Estados Unidos hay muchos programas para incrementar el número de personas que vienen de grupos underrepresented como hispanos, gente afroamericana y sobre todo mujeres. Y actualmente en Oak Ridge soy chair presidenta del grupo de Women in Physical Sciences y pues tratamos de incrementar la representación en las ciencias porque pues nada más para armar nuestro grupito pues siempre es muy difícil encontrar a otras mujeres que trabajen en nuestro campo y pues tratamos de hacer eventos para no nada más conocernos, pero pues también para atraer más mujeres a nuestro campo, porque pues sí es difícil desde infraestructura y logística en la división de física, por ejemplo, creo que hay o sea, en el edificio ha de haber como alrededor de 4 baños para hombres y para mujeres nada más hay uno porque pues en la Segunda Guerra Mundial no se acostumbraba que las mujeres fueran a trabajar al laboratorio, ¿no? Entonces pues cambiar un poquito esa dinámica y esa, I guess, percepción de las mujeres en la ciencia.
Sí, sí, precisamente, yo creo que esa es una labor que a todos nos concierne pues como gente que estamos trabajando en estas áreas de ciencia. Como profesor, yo trato de motivar también muchísimo a las mujeres porque sé de los bajos porcentajes de mujeres participando en proyectos de ciencia. Me gusta mucho que se incorporen porque creo que es grandioso tener un grupo en donde se compare el número de hombres con el número de mujeres. Eso se me hace muy chévere. La verdad, las participaciones siempre de las mujeres son muy, muy buenas. Pero bueno, por otro lado, nos preguntan también dice, ¿Do you have any references for particle track reconstruction using D-Wave?
Yes, a bunch.
Okay,
Um,
tell us.
I have like 10 that I could probably just tell you the names. But if you're really looking at a quantum advantage, the systems for the quantum computing systems are just not big enough to deal with the amount of information coming from trackers in collider experiments. So we're still looking. You can see what people have done, but still nothing promising.
Okay.
I have a paper that it's on review right now, but we just haven't been able to use quantum computers for tracking.
Okay. Good. I have another question. In this talk, you talk us about the about the I mean experimental analysis. So my question is, do you think it's very interesting to tackle this kind of problems in a theoretical view?
So what you're saying is instead of doing data analysis, working on the actual simulation of quantum systems.
Yeah, yeah.
Yeah, that's one of the fields that I really want to get into. Um, there are some papers by people doing neutrino system calculations, quantum gravity. I think it's super interesting. Just any field theory that can be simulated with quantum computers, I think it's really exciting. Because just as Feynman said, if we really want to study quantum mechanics, we should really use quantum computers for that.
Okay, thank you. We have another question. Is let me see. How is the implementation of the TSP different in quantum computation? Um, I don't know what is TSP. Sorry.
Traveling salesman problem.
Ah, yeah, I think so.
Yeah, I try to avoid showing the QO that we use for the traveling salesman problem because at least for our formulation, it's huge. So it will take me just it will probably be the size of the standard model Lagrangian to give you an idea. But if you want a general formulation, there's a paper by Andrew Lucas, and it's called QO formulations for NP-hard problems, and they have a general formulation that it's very simple.
Okay, sorry. Let me read other question. Can I found your paper on archive?
Not right now. I have two papers that are like on review, but they will not be on the archive until they are published on the journal that we're getting them into. If you're interested in like a specific thing, I could probably ask, but as of right now, I don't think we're having the papers on the archive.
Okay, so one more question. I don't know. Sandy Del Mar says traveling salesman problem, but I don't know if this is a question or sorry, Sandy. Could you explain more, please? Okay. So yeah. Okay. En español. Hola, Quantum Hispano se está reportando. Saludos a todos los hermanos de Quantum Hispano. Bienvenidos y desde luego la comunidad está abierta para estos futuros eventos que, por cierto, vamos a estar llevando en futuras ocasiones. Estaremos al menos una vez al mes en este seminario. Hoy hemos tenido una grandiosa charla. Realmente a mí me apasiona muchísimo esto porque parte de mi formación, bueno, de hecho toda mi formación en investigación ha sido en altas energías y ahorita estoy introduciendo algunos temas de computación cuántica y quantum machine learning que nunca sabía cómo se produce en español. Pero bueno, muchísimas gracias por la plática, Andrea. Detrás, este sería un buen momento para mencionar que aquí en México somos una comunidad en donde afortunadamente yo estoy ahí metido con varios colaboradores, colegas que estamos promoviendo temas de computación cuántica, temas de quantum machine learning y aplicaciones también en otras áreas. Posteriormente tendremos invitados de diferentes partes del mundo. Intentaremos de promover muchísimo por redes sociales, pero siempre estamos muy, muy abiertos y muy agradecidos si también otras comunidades también nos ayudan a promover este tipo de eventos que yo siento son muy importantes para nuestra comunidad en Latinoamérica. Am, Déjame ver si hay otro comentario o pregunta. Dice Sandy del Mar que estaba comentando respecto al Traveling Salesman Problem. Estaba comentando. Está muy interesante también esta parte. Yo no, hay temas que no estaba tan cercano. Y bueno, no sé si haya algo más por agregar de parte también de la comunidad de QMexico. Detrás hay un grupo bastante amplio de colegas. No sé si alguien nos quiera enviar alguna pregunta más o algo que se esté escapando en este momento. Mientras, Andrea, pues de verdad que está muy chévere tus temas de investigación, muy padres. Esperemos que se puedan dar también futuras colaboraciones.
Claro. Muchas gracias a ustedes por invitarme.
Am, ok, déjame ver, no sé si Aaron nos pudiera apoyar dejando el perfil de Andrea también aquí podría ser en el en vivo o puede ser una liga. Mientras también les comento un poquitito de la vida de Andrea, ella ahorita está como Wigner Fellow en Oak en Rich National Laboratory. Y ella ha colaborado con diferentes organizaciones del CERN, bueno, al menos sabemos de una, y bueno, si gustan también contactarla, seguirla, nos están dejando ahorita, podemos, no sé, a ver, Aaron, si nos puedes apoyar con esa parte, compartir el perfil de Andrea, o bueno, también creo que yo lo tengo por acá, lo podemos compartir. Am, a ver, ahí no lo encuentro. Ah, ya lo encontré. Gracias. Ahorita lo compartimos aquí también por el en vivo para que para que sigan a Andrea y sus áreas de investigación. Bien, pues también te agradecen mucho en el en vivo, Andrea, de parte de Jesús. Muchas gracias por compartir este excelente conocimiento. Eh, Muy, muy chévere, dice, bueno, en pocas palabras. Y bueno, ahí ya tenemos el Twitter de Andrea también en el en vivo. Bien. ¿Más por agregar, algo más por agregar, Andrea?
Pues no, muchas gracias. Sigan con el momento que ya llevan, porque pues de verdad que la computación cuántica es el futuro, ¿no? Y
Sí,
además, pues, ¿cómo se dice? Take advantage de todas las herramientas que tienen ahorita. Yo creo que para aprender Quantum todo ahorita es open source, los libros, los tutoriales, hay muchas herramientas para enseñarse uno mismo, no hay que ir a la escuela ni tener un degree.
sí, es cierto. Muy bien. Pues nuevamente, muchísimas gracias. De verdad que es muy, muy excitante, muy chévere estos temas que estás trabajando, Andrea. Agradecemos también a nuestra audiencia, también a nuestros colegas que, como mencioné, aquí en México es una comunidad bastante amplia de colaboradores. Seguramente nos van a encontrar también en redes sociales y en este canal de YouTube vamos a tener nuestras siguientes sesiones. Bueno, pues creo que eso es todo por el momento. Muchas gracias por todo, por toda la participación de todos. Muchas gracias también, Andrea, nuevamente.
Gracias. Bye.
Hasta la próxima. Bye bye.